Start with a little bit of review again before we get back to aromaticity. So this unit's primary focus was looking at a lot of addition reactions, and we started with electrophile additions. And if we break through that language, our addition is looking at a pi bond reacting with an electrophile. That reaction process is that the pi bond shares electrons with the electrophile. Okay, what this ultimately meant for us as far as functional groups is that we were looking at non-polar pi bonds, which then translates to our alkenes and our alkynes. We then also navigated into our, let's go ahead and use this one, our nucleophile additions. And in nucleophile additions, we're looking again at a nucleophile, so a source of electrons, reacting with a pi bond, except this time the electrons go towards the pi bond. This should seem a little bit weird if we were going to consider our alkenes or our alkynes, because if we looked at a polar pi bond or a non-polar pi bond, since there is no polarity between that primarily acts as a source of electrons. So if we're moving to nucleophile additions, this seems very counterintuitive because you're taking a source of electrons and reacting it with a source of electrons. Okay, but the reason we can get away with it, or the reason why it works, is that we end up reacting it with polar pi bonds. So the polar pi bonds end up being carbonyls is our primary category, but there's tons of kind of things. So we can go with carbonyls, and we'll call them imines. Don't stress about knowing that name or not. But a carbonyl, or a polar pi bond, is now carbon and an electronegative element. And if it was nitrogen, that would be the imine. If it was oxygen, that would be our carbonyl. We didn't specify necessarily what was connected out here, okay, at least right away. When you go through and look at the reagents, though, those kind of question marks became rather quickly carbon or carbon and hydrogen, okay, which left us with carbonyls specifically as aldehydes or ketones. Okay, why the sudden change in reactivity? Well, that sudden change has to do with the polarity of that bond. Because that bond is polar, we could look at the resonance structure, and the resonance structure is going to generate kind of two things. One, a negative carbon, and the other end, a negative oxygen, and at the other end, a positive carbon. Deciding which of those two is more reactive ultimately goes all the way back to Unit 1 when we talked about drawing Lewis structures. And the thing that we were most concerned about when drawing Lewis structures is complete octets. So if we're looking at a polar pi bond, the primary chemistry has to focus on where we're missing an octet. That carbon has a missing octet, and therefore that's where the primary chemistry is. Okay? That missing octet means that the polar pi bond, all the way back at the beginning, is primarily acting as an electrophile, which is why nucleophiles react with them. Kind of, sort of. We then take it kind of a step further. Let's go with orange. And we moved to nucleophile additions followed by nucleophile eliminations. Oops. Can't spell elimination. Those are typically abbreviated NAE, or at least that's how I've abbreviated them, as nucleophile addition eliminations. Okay? These are still involving a nucleophile doing the breaking of your pi bond. Okay? So they're still coming in and attacking that pi bond. But there's some extra chemistry. Okay? They're followed very quickly by a second step that results in the formation of a pi bond, and I have no way of showing arrows for this. Yeah, I don't think there's a clean way for me to show arrows for this particular system, okay, where changing my symbol notation. The pi bond is reformed. So we have loss of a pi bond, and then we have a second step where we gain the pi bond back. Okay, that gain of the pi bond is your elimination. We're following the same core chemistry, okay, which means, again, we're going to have polar pi bonds. But these polar pi bonds are slightly different than the nucleophile addition carbonyls and imines. These polar pi bonds, and carbonyl is the primary category for these carbonyls with leaving groups. The aldehydes and ketones don't have leaving groups. Carbon and hydrogen are not good at taking electrons away from that carbonyl functional group, and so it doesn't work out. If we look at what these new functional groups look like, they're the polar pi bond, our carbonyl, except now we have a leaving group connected to it. So our reaction happens by breaking the pi bond first, then we reform the pi bond and we eject the leaving group. That is our whole nucleophile addition, nucleophile elimination. Right? There is a whole ranking system, the whole ladder behind all of those reactivities. That's what we talked about Wednesday. Okay? It's still that same kind of missing octet issue, but what we end up looking at for these is the varying leaving groups, or the varying leaving groups that you could have, and how they affect the electrophilic carbon. Okay? So those are our three primary classes of reactions that we've gone through with a whole bunch of different reagents. One of the things that I do want to address or kind of talk through is that there's no way that I would reasonably expect you to have all of those reagents memorized by the time the final rolls around. Okay? So again, what I'm looking for are the broad strokes behind it. Do you understand you're looking at a polar pi bond, which means it needs to be reacting with a nucleophile? Do you understand that you're looking at a nonpolar pi bond? That means it needs to react with an electrophile. Okay? Within each of those systems, there are reagents that will match to those chemistries. Right? So for instance, with our electrophile additions, we could look at hydrogens being an electrophile. For hydrogens to be positive, they would need to be connected to an electronegative element. So what you're seeing is large positives and negatives established from that. If we look at an alkene, all the way to the far right, my bad. Okay, that pi bond can still do resonance, generating partial positives and partial negatives. Depending on symmetry of the alkene, you would expect the positive to build at one position versus the other. You now have positives and negatives that can match the positive and negatives of the reagent. So it's a question of finding positives and negatives in both places, both in the reagent and within the functional group. All I want you to be able to do is to recognize that matching and that pairing to be able to generate an answer. That's my primary driving force. Okay? I don't expect you to be able to look at a complex reagent and be able to tell me exactly what's going to happen out of this particular sequence of reagents or reactions. But what I expect you to be able to do is to look at the patterns both within the answer choices and within the reagents to be able to match positives and negatives appropriately. Kind of, sort of? Okay. Does this mean you won't see reagent questions? Absolutely not. You will absolutely see reagent questions, but they're going to be very, very limited in scope, particularly from Unit 4. Unit 3, Unit 2, Unit 1, any reagent that's been dropped there, you're supposed to know all the detailed aspects behind those. That's what those tests and units were about. Unit 4 is the broad strokes. What are these primary functional groups? How do they react as a class? And understand some of the basics behind it. Kind of, sort of? Okay. So So that's our whirlwind review of everything so far in Unit 4, which should be familiar because we've been doing this at each and every single one of our lectures, is summarizing everything that's been covered to that point. What we're now going to bring in is a new functional group, if you will. And within that, what I'm going to do is get rid of the bottom one, because the bottom one is really just a special case of the nucleophile addition. And what we're going to do is talk about this concept of aromaticity. Aromaticity primarily drives off of the special properties of benzene. Benzene is a 6-membered ring with 3 double bonds alternating around it. One of the special characteristics of benzene is that we can move those pi electrons via resonance. And we can draw another resonance structure, admittedly a little bit sloppy there, where the double bonds have moved around the ring. Okay, remember, when we draw resonance, our structure is pinned. We can't spin, flip, or rotate it. It's locked in place. Okay, why is this special to us? If we consider the resonance structure for an alkene, and we draw its resonance, what we're going to end up seeing is the formation of charges, negative and positive. We saw the same thing if we consider what happens with our also generate this positive and negative. But the aromatic ring, when we look at its resonance, does not generate charge. What does that suggest about the stability of the original ring? Yeah, our aromatic rings are incredibly stable. So when we look at a benzene structure, we have to be a little bit kind of careful or cognizant to not match it to any of the other systems that we've looked at, because it's not a polar pi bond and it's not really a nonpolar pi bond. I mean, it is a nonpolar pi bond, but the nonpolar pi bond chemistry does not apply to benzene. And that's because it is so much more stable. Okay? So much more so that when you see a benzene ring, what you should immediately reflex to thinking is it doesn't react. Okay? And if we think back to our substitution chapter, even when we put a leaving group on it, we still suggest it does not react. Okay? And that's kind of an interesting phenomenon that has to do ultimately with the resonance within that. Somebody went through and got super excited about benzene and tried to figure out why it was so stable, and does that stability apply to other molecules? Okay? And it turns out it does. Okay? So if we build this out, what we encounter is, I know, a god-awful amount of text. But what this goes through to say is that if we have an aromatic structure, it satisfies certain rules. Okay, so we'll get rid of these other ones for the moment because we don't need to see those. So if we look at our benzene structure, and this is going to work with chlorobenzene whether or not, is that we would look within our ring and we would notice that it has a fully conjugated ring with overlapping p orbitals. What does that ultimately mean? That's a bunch of fancy words. So it means we have to have a ring. So if I went through and I drew, 1, 2, 3, 4, 5, 6, versus that, okay, the right one is actually a ring, whereas the other one is not a ring. Even if I went through and tweaked that other one, can't complete that line, and did that, we still have 6 carbons, but it's still not a ring. So it has to have a fully connected ring. But it says other things. It says overlapping p orbitals. What does that mean has to be the case on each of these carbons? There's a couple answers that can come out of that. easy answer and there's a hard answer. Okay, I'll give you the easy answer. There has to be a p orbital there. Okay? Overlapping p orbitals. That means there has to be a p orbital at every single one of those positions. Okay? If we're looking this as a flat molecule, those p orbitals would be coming in and out of the plane at us. Okay, so not easy to see. So what we could try to do is we could pretend that we could pull this front carbon kind of up at an angle, kind of towards us. So that we can kind of see it from the side. And we must have those p orbitals. Kind of make sense? Okay, so if that was the easy answer, what's the hard answer? What else is special about each and every single one of those carbons? Little clue, it's a question straight out of Unit 1. Which is a nice way to ask a question about Unit 4 content within Unit 1 scenarios. That is fair. I did not actually think of that, but you're correct. Every single one of them has one hydrogen. I'm not going to draw all the hydrogens. What else could we say is true? Follow up to the one hydrogen kind of comment. There's a pseudo hint by darkening those lines. Do better. There you go. We could look at the geometry. All of those are trigonal planar molecules. So if we look at this molecule, it is entirely flat. And then what else? Probably the hardest. Everybody struggles with it. It's a subtle hint. Makes more sense when it's filled in. What was that? Getting right to the orbitals. Yeah, what's the hybridization? It would be sp2. So remember our cheat is we could look at the superscripts. There's an implied 1 in front of the sulfur. That's 1 plus 2 is 3, which gets us 3 electron groups, which ties back to the 3 that we're writing there, which also gives us the trigonal planar geometry. So we could go through and reference each of those carbons being sp2 hybridized. Okay? That can get tricky. I don't think I'm going to make it tricky, but that could get tricky. Okay? The next part, and this is arguably why I don't want to make it tricky, is that we encounter this weird rule. Okay? It must also meet what's known as Huckel's rule. Huckel was one of the people that discovered this phenomenon, and so that's why it's tied to him. Okay? What Huckel's rule is that you're looking at an odd number of electron pairs. Okay, so when we look at the benzene structure, so now the actual drawing of benzene, not my crude hand drawing one, because my hand drawing one doesn't show the odd number of pi electrons. If we go up and look at the benzene, I have 1 pair, 2 pairs, 3 pairs. 3 pairs of electrons, or pi electrons, is an odd number. Benzene satisfies this rule. That's what this is trying to say. Okay? You will encounter that there's also this weird extra kind of formula that comes out of this. Blame a mathematician for this. Is that if we look at the number of electrons it follows this pattern of 4n plus 2, where n is any whole number integer. Okay? So for benzene, n is what? This is where we're going to be careful. So 3. So 4 times 3 is 12 plus 2 is 14. How many pi electrons do we have in benzene? Careful, we have 3 pi bonds. We have 6 pi electrons. Okay, so this 4n plus 2 is counting all of the pi electrons. There's 6. So n can't be 3, because if n was 3, we'd get 14 pi electrons. I only have 6. So what is n in the case of benzene? 1. Okay? That's all that system is really saying. So if we really kind of extrapolate Huckel's rule out, we can get n equal to 0, which means we have 2 pi electrons. N equals 1, 6. N equals 2, 10. N equals 3, we already did. 14, n equals 5. 18. And if you're trying to do all the math, what you can note is a different pattern. What happens as you go through each of these? You just add 4 electrons. That's all it is. So what this rule is effectively saying is that if we look at a cyclic structure that has pi bonds, does it have these number of electrons? If it does, it is aromatic. What does it mean if it's aromatic? It's incredibly stable and is effectively like benzene and is very unreactive. That's all we really want out of it. Okay? So let's look at a weird example. Would we count this structure as aromatic? And if you're wondering what structure, I mean the triangle. The triangle is a structure. It's valid. What was the head shake? No, Lindsay. You can just be like, I'm overwhelmed. I don't want to answer. That's fine.
It's not a ring.
Huh?
It's not a ring. It's a triangle.
Define a ring.
Bless you.
It's hard, isn't it?
It is.
It's a carbon chain that loops back on itself and is interconnected. Well, what is the carbon chain here? It's 3 carbons. Do they loop back on each other?
Yes.
Is that a ring?
Yeah.
Yeah. We may not like the ring, beside the point. It is still absolutely a ring. Okay. So our first rule is a fully conjugated ring with overlapping p orbitals. There were a couple things within that. The first part that at least Lindsay noticed was it needs to be a ring. Okay, this is a ring. Should we move on to Huckel's rule yet? No, we shouldn't. Why not? Rule 1 says ring and what else? Okay, it depends how you want to look at it. Overlapping p orbitals. Okay, and remember the benzene structure we looked at? Every single one of the carbons was trigonal planar. We could go with that. I'm fine with that. So let's work with that. Are all of our carbons in this structure trigonal planar? Too long a pause. Let's look at the blue carbon. How many groups of electrons are around it?
2.
How many electrons are around it? So if you're going to say 2,
5.
stick with it. Try again. There would be 6 electrons around it. That would be a problem considering octet. If that's a neutral carbon, its octet must be satisfied. Since there's no charge specified, the octet is satisfied. So you're missing something. What are you missing? There's a hydrogen. How many groups of electrons are around it? 3. Is it trigonal planar?
Yes.
It is indeed. How about the red carbon?
Same.
Same deal. How about the green carbon? No? Okay, I heard Kimball first, so we'll go with you. What do you...
There's 2 flat hydrogens. So
The-
that'd be, tetrahedral.
Awesome. Way to push all the way to the extreme. Yep. So that green one currently is tetrahedral because it has 4 groups of electrons around it. Okay? Because it has to have those 2 hydrogens to satisfy that octet. Okay? Because it is uncharged. So that goes back to, did we memorize or have we applied all of those bonding patterns in Unit 1? Okay, so what does that mean? Not all of the atoms are trigonal planar, which means we don't have overlapping p orbitals. Okay, and if we don't have overlapping p orbitals, it's not aromatic. Okay, or we're just going to have to use that word for the moment. Okay, because what we'll see in a second is it gets a little bit more complicated. So let's make a modification. I'm going to get rid of one of those hydrogens. But if I get rid of a hydrogen, that carbon would be missing its octet, right? And if it's missing its octet, it would need to be charged. So let's make it charged. Is it trigonal planar now? I can tell how much you really didn't like that answer. Like I saw a flinch in your face, like, oh, this is gross. Okay? We don't care about whether it's pretty or not. We're just evaluating the structures. Okay? And yeah, it is trigonal planar. What does that mean? It's a fully conjugated ring and it has overlapping p orbitals. So we don't have to like it, but rule 1 is satisfied. What is rule 2? Does it have an odd number of electron pairs, of pi electron pairs?
Yes.
Yeah, it has 1 pi bond, okay, or 1 pi pair. So it does satisfy that it has an odd number. What are the total number of pi electrons? 2. Was that part of Huckel's rule? Yeah, it was. So this structure is aromatic, which is interesting. It's charged, and yet it doesn't react. That's kind of cool, or at least I think that's kind of cool. We have this charged molecule that actually does not want to react. That's fascinating, okay? And that's because it satisfies this aromatic system, okay, or these aromatic rules. Okay? I did say it gets a little bit more complicated, so let's make it a little bit more complicated. And particular, what the first structure we looked at, or the one with the tetrahedral green carbon, was saying it's not aromatic. And this is where we encounter some weird kind of phrasing systems. Okay? Because we'll encounter another set of rules known as anti-aromatic. And due to a glitch in how this system was counting, they called those 3, 4, but that's really rules 1 and 2. Okay? So we could look at a system that has a fully conjugated ring of overlapping p orbitals, okay, and an even number of electron pairs. Okay, so the structure we're showing here gets a little bit complicated based off of the rule set you guys have been using, trigonal planar. Okay, it gets a bit confusing because that's not really trigonal planar, it's more tetrahedral, but those lone pair electrons can resonate inwards, causing those to move up there. So those electrons do have the option to resonate through that molecule. And this is where trying to look for hybridization can help out. Okay? And one of the things that kind of makes this complicated is an sp3 atom can act like an sp2. Okay? Which we've seen a lot of. That's resonance. That's what's happening when you move lone pair electrons into a pi system. The sp3 atom acts as an sp2. Okay? What does that mean for the reactivity of this molecule? Well, it's anti-aromatic. It's not aromatic. It's anti-aromatic. Aromatic meant incredibly stable. What does anti-aromatic mean?
Nicely. Yes.
It's the opposite, because it's anti.
Non-stable.
Very unstable. Anti-aromatic compounds are very reactive. Okay? So much so that the structures themselves will sometimes try and bend into weird geometries to prevent them from being in this anti-aromatic system, to try and break rule 1, overlapping p orbitals. So they'll bend the shape into odd systems so the p orbitals don't overlap, because if they did overlap, it would make the structure more reactive. With a tiny 3-membered ring, that doesn't happen very often because there's no place to really bend. So that structure just ends up being very, very, very reactive. The last kind of category that can kind of come out of this is these non-aromatic systems. Same deal, numbering went weird in the copy-paste. This is 1, 2. Non-aromatic systems somehow invalidate the rules above. Okay? So if we look at just a simple chain, well, it's not a ring. Because it's not a ring, it can't be aromatic or anti-aromatic. Okay? It doesn't have overlapping p orbitals. Also invalidates it. If we looked at the initial, or one of the initial examples with that 3-membered ring, this structure, that green carbon was tetrahedral. Since it's missing those overlapping p orbitals, it also doesn't satisfy the rule set. Okay, so that molecule becomes non-aromatic. The last category, which you will not see, and very arguably you won't see most of this, you might see a question, which of these is aromatic, but that's it. Okay, you could see something like a trick question where the structure, as I just described with the anti-aromatic, bends itself into a weird shape to prevent one of the previous rule 1s from existing. Okay, the one case for that I know of for certain, which I'm going to do an awful job drawing. Actually, it's not that bad because I drew it this way. Is the 8-membered ring with 4 double bonds. All of those are trigonal planar atoms, so we would expect it to adopt a planar structure. Okay, and in that planar system, we would then go through and count our electrons. How many electrons or pairs of electrons do we have in our pi system? 1, 2, 3, 4. It's not an odd number, so that's not our aromatic. It's our anti-aromatic. Okay? So that structure would be considered anti-aromatic, except anti-aromatic is very unstable. Because it's a ring structure, and a large enough ring structure, what it ends up doing is puckering a little bit. And if we look at it from the side, it does this. And by bending kind of into that pseudo boat shape, that prevents the overlap of the p orbitals. So the molecule itself isn't actually anti-aromatic, it adopts a non-aromatic system. The structure prevents itself from being unstable. Just kind of neat. Kind of, sort of. Big lesson, aromatic. That's our big kind of piece out of this, is that structures that satisfy the aromatic rules are incredibly stable and effectively non-reactive, which is how we've kind of existed throughout the entire semester. That's the biggest piece I want you to get away with. Okay? So this can be one of the reasons why aromatic compounds are dangerous, okay? Because they're very planar. And since they're unreactive, they can situate themselves into varying spaces. We talked about why sunscreens could be dangerous, and they had benzene structures. Those benzene structures could insert themselves into DNA, cause a pucker, and increase the chances of making mutations. Okay? That's an artifact of the extreme stability of the aromatic structure. Okay? Whereas other things can be dangerous, but for other reasons, like alcohol. Okay? Alcohol gives us a buzz. Why? Because it's killing brain cells. Okay? It's not inserting itself into DNA to cause mutations, but it's forming an aldehyde, which is what's killing the brain cells, okay, that eventually turns into a carboxylic acid that we can then urinate out. Methanol, instead of ethanol, becomes very, very dangerous because its first oxidation step is formaldehyde. And formaldehyde in the brain does lots of damage, okay, particularly in eyes as well, which is why you can go blind. Okay? So we're looking at different mechanisms behind these systems. Aromatic structures, for the most part, are acting just as kind of things to change overall shapes. They aren't doing chemical reactions in biological systems, most biological systems. Kind of, sort of. Which is one of the reasons why I think it's a bit odd to talk about aromatic structures in a class like this, or really any organic chemistry class, because the vast majority of students that are taking organic chemistry are trying to do what?
Pass it. Go to the next
To go on to what next class?
biochemistry.
They're all concerned about health things, okay? Or health genres. And in those health genres, we're less focused on the aromatic structures because the aromatic structures aren't doing anything chemically. Okay? So they're incredibly powerful, they're useful within synthesis, but that synthesis is mostly driven to synthetic chemists and not to biological systems. Okay? Which sets us up kind of for the next part of this, which is the video that you guys were supposed to be watching, right? Which is electrophilic aromatic substitution. We're going to do a quick kind of walkthrough on that. I just realized that I had some examples up here, so we'll go through and look at some aromatic examples here in a second. Okay? But then we'll go through and look at the overarching electrophilic aromatic substitution, which is a chemical reaction with our benzene structures. Okay? And then we'll talk about some of the kind of side effects behind those. And then we're done. Content-wise, that's it. Right? And we'll be left with just asking and answering questions. So, can it be aromatic? We already did benzene, so let's erase that one. How about the next one? What do we think? Is it a fully conjugated ring with overlapping p orbitals? Yes. Does it meet Huckel's rule? No. Which means? It's anti. How about the next one? It is not anti. That green carbon at the top had no charge, which means there's two implied hydrogens, which means no p orbital, which means that structure is non-aromatic. How about the next one? Now that we have a charge, it only has one implied hydrogen. That becomes anti, an even number of pi electrons. Because I don't see the sister to this one. What if we did that? This top atom is sp3 hybridized, but what did we say sp3 could do? it can act like sp2 through resonance. So what does that mean for the next system? Well, it is now a fully conjugated ring with overlapping p orbitals. Does it meet Huckel's rule? Does it have an odd number of electron pairs? You might go through and say, well, it only has 2 electron pairs in the pi system, right? There's only 2 double bonds. Except that lone pair is also contributing to this. So while it is not currently in a pi bond, if I drew the resonance structure, I would see that it is indeed part of that pi system, which means I do need to count the lone pair in it, which means I've got 6 pi electrons. That does satisfy our system. This is aromatic. Kind of, sort of? How about the next one? What's that? Why is it none? We need that ring. I wasn't trying to cross out ring. Needs to be a ring. Next one. Why?
Because there's right?
So an even amount, so you're saying here and here.
Yeah. But then two
There's 2 lone pairs. How many lone pairs? So for the lone pairs to count, what has to be true? It has to be an sp3 atom. Is that oxygen sp3 atom hybridized? This goes back to unit 1, being able to identify our hybridization patterns. Does it have 4 groups of electrons? Yeah.
Like that.
Which means, is it sp3 hybridized?
Yeah.
Yeah. So one of those pairs can count. The other pair cannot count because as soon as one rotates in, the other one rotates perpendicular to the pi system and so cannot be involved in the resonance. So one pair counts, the other 2 are pi systems, which means how many electrons do we have? 3 pairs of electrons, which means, say again? And it's going to come down to how you count. Okay? Huckel's rule is 4n plus 2 total pi electrons. And so if you're saying 3 pairs, that's 6. 6 is aromatic. Or it's an odd pair of electrons. 3 pairs is odd. Make sense? Ish. Last one. So for sure, what is the hybridization of this nitrogen? How many groups of electrons are around it? And if it's 3 groups of electrons around it, is it sp3?
SB2.
It's sp2. If it's sp2, can I count that lone pair? Nope. What's the hybridization of the top one?
SB3.
sp3, can I count the lone pair?
Yes.
Yep. How many electrons?
2.
I think you're saying 2 because you're counting the lone pair.
Yeah.
Yeah. Whoop! Ah! As I throw the pen, which gets us a total of 6 electrons, which puts us right back in that aromatic category. Okay. So all the molecules that are aromatic in this system would be incredibly stable and effectively unreactive. Okay. The non-aromatics are just normal reactivity, so we would expect those to react as alkenes. The anti-aromatic would effectively be superalkenes. They're incredibly reactive, and we want to neutralize that charge as fast as humanly possible. Kind of, sort of? Okay. So what we'll move to is now the kind of contradiction in terms. We just went through and said aromatics don't react, and yet what are we going to do?
Do the reaction.
We're going to have them react. Okay? Which does seem kind of contradictory, but again, it's coming from kind of a different place. Consider that all things can react. Right? But the question becomes is how much energy do we have to put in to force that chemical reaction? So what we're going to go through and look at is the generic system first to explain how it can go through and react. But for it to react, we have to ensure that the proper system is in place. We have to ensure we're using the proper reagents. Those reagents tend to be higher in energy so that it can force the formation of this reaction. Okay? It's not just a simple, oh, we just mix these things and we're done. We very much so have to force the conditions to work. So let's push through by taking a look at the name. We can start with the very first part. It says electrophilic. What does electrophilic mean? It accepts electrons. So what would be a good symbol to represent our electrophilic atom? I would argue two symbols. I just need a placeholder first. How about an E? I like an E. I've had people give me absurd things, and so there's varying versions of this lecture where I've got very strange drawings. It's like, oh, I want it to be a pineapple, really? Okay. Okay, but now the second part of it, how do I know it's acting as an electrophile? And don't tell me because I wrote E. If it's accepting electrons, what might be a characteristic that we would expect on our E?
A lone pair?
Do lone pairs accept electrons?
No.
Lone pairs would donate electrons, which would make it
A base.
a base or a nucleophile. I want it to be an electrophile. So what would be a characteristic of an electrophile? It should be positively charged. It wants electrons to be drawn towards it. So more than likely we're looking at a positive. Particularly if we're going to now react it with an aromatic. Well, what is an aromatic? What's our classic aromatic structure?
A ring.
Is that aromatic? We still need the double bonds on the inside. Okay? Would we expect the aromatic ring to be the electrophile? Why not? That was an aggressive no. That was a good one. I liked it.
Isn't it? Is it very stable?
It is very stable, so that's explaining why it should not react. But what I'm asking is, let's say it does react, how would I predict the aromatic ring to act? Would I expect it to donate electrons or accept electrons?
Set.
Why?
Because or no, what's not going to donate to the electrophile, is it?
Irrelevant. How would I expect that to react?
Like it's your substrate.
It is the substrate. What should it do? Should it accept more electrons or should it donate electrons?
It's going to accept more
Okay, why?
because it's going to be like a base or something to build off of. Not base like.
Okay, I see what you're
reactions,
saying.
but, like,
But something to build off of, I could have it act as a nucleophile or an electrophile, and it's still building off of it. Let's try it differently. How do we expect an alkene to react? Or for that matter, a carbonyl?
Something's gonna make the carbon positive or negative usually.
So that statement in and of itself is problematic, because what you're saying is something from the outside does this. I asked how the carbonyl reacts. I don't care what's on the outside. I care what's on the inside. When I look at the carbonyl, how would I predict it to react? When I look at the alkene, how would I predict it to react? What I'm trying to do is look at a structure and see what is inherently reactive about it. That's the functional chemistry that you should be pushing to. Not, well, when this thing comes in, it does this. Okay? You're now looking at a different system. You've manipulated the argument in your favor. Just look at the structure itself.
The oxygen would be more reactive than the carbon because it's more electronegative.
So the oxygen is more electronegative, so we would expect the oxygen to take the electrons away, right?
Yeah.
Did it react yet? No, all you're suggesting is that we should draw our resonance structure. Did I draw a resonance structure? Kind of is an appropriate adjustment there. I would argue no, I did not draw the resonance structure. I have failed in my duty in drawing a resonance structure. What do I need to fix?
The octet, the carbon.
Sort of. Elaborate.
You need to transfer one pair into a bond.
So I could take the lone pair from the oxygen right back. All you're taking me back is the previous structure.
I guess you're right.
That oxygen has gained electrons and is therefore negative. That carbon has lost electrons and is therefore positive. Now I've drawn an appropriate resonance structure. Resonance structure is about moving electrons and drawing a proper Lewis structure. We did not have a proper Lewis structure because we didn't show the charges. Once the charges are on there, we now have a proper Lewis structure. Now with that proper Lewis structure, we could ask the question, what's reactive? The carbonyl is an interesting dilemma because we have both an electron source and a place that is missing electrons. Which one is our priority?
Well, that's missing.
The one that's missing. Octet satisfaction is our number one rule. So when we go through and look at the carbonyl, how does the carbonyl react? It's an electrophile. It's an electrophile because I can see that it's a polar pi bond and it has resonance. That resonance system allows me to see the carbon is missing electrons. Since it is missing its octet, I must satisfy that octet. I'm going to add a nucleophile. Now I know that a nucleophile comes in. Okay? Because I've established what the core chemistry is, first and foremost. Can I still have it act and react as an electrophile? I absolutely can. There's a negative oxygen. Does that mean that's its core chemistry? No, it does not. Its core chemistry is that it is an electrophile. And we can see that by using the resonance. The polar pi bond, phenomenal hint to help us predict that chemistry. So when we look at a carbonyl, we say electrophile. Cool. What do you see when you see an alkene? Do you get the polarity? No. Resonance only works if we've got the polarity. So when we look at that alkene, that blue structure, what do we see? I see two C's. The two C's are irrelevant to the argument. I see two lines. What do those lines represent? Electrons. Are those electrons the same? No, they are not. And we can show that by making it different colors. How are they different? Why is the red one different from the blue? And don't tell me because of the colors. I understand. The orbitals being used to make those bonds. Yeah, what orbitals are being used to make them? And the drawing does not tell you, it's implied. Once you've specified one, you know the other. So if you can tell me orbitals for either color, it doesn't matter.
Sigma and pi, so S and P.
Okay. We've got one that's a sigma bond because it's using S-type orbitals. Okay, for a carbon or an alkene, those are typically sp2 type orbitals. If we move to the blue one is pi bond using p-type orbitals. So what is the difference between our sigma and our pi bond, other than the types of orbitals? Or we could push all the way to the orbitals. What's the difference between an s orbital and a p orbital?
Stability
Yes.
or strength.
Don't go strength. Strength's gonna backfire on you.
Whether or not you can.
Which one's more stable? Let's try that.
The sigma would be more stable.
Oh, awesome. The sigma's more stable. Of course, what am I going to follow it with? Why? What orbitals are being used to make the sigma?
S and P.
Careful. S-type. So you can say S and P if you're saying sp2 or sp or sp3. Okay, I would argue those are all S-type. And we look at the bond, when we look at S-type orbitals, the bond is a direct overlap, which means what happens when we rotate the bond? What happens to the overlap? Nothing. It stays overlapped. What happens with the pi bond? What orbitals make the pi bond? P-type. The p-type never directly overlap. All the way back to unit 1. That's our p orbitals occupying that same space, which is why if we tried to rotate it, what happens to the bond? It breaks because the overlap isn't there, which means the p orbitals are necessarily higher in energy. Why does that become important? I want to know how this molecule reacts. If I get no resonance, I can't say the electrons are going to one side or another, which means I see no obvious negatives and positives. All I see is that I have electrons in a high energy orbital, which means those electrons can do what? Try to go to a low energy orbital somewhere else, which means the alkene needs to do what with its electrons? It must donate them, which means the alkene will act as, bingo, a nucleophile. And it's donating the electrons to an electrophile, which means when we look at alkenes, what chemistry do we see? We see electrophile addition, because the alkene's going to react with electrophiles. All of that chemistry, all of those patterns stack, and they stay constant all the way through. That's the lovely part of organic chemistry. If we now go back to our aromatic structure, how would we predict it to react? What do we see when we look at the aromatic structure?
Carbon to carbon double bonds.
Carbon to carbon double bonds. What is the double bond? Ooh, okay. It looks an awful lot like an alkene, but we just learned that due to the resonance, it's not the same reactivity as an alkene. Would we predict it to have the same chemistry as an alkene? There's no polarity, so the only thing we've got there are p orbital electrons. What would those p orbital electrons likely do? Donate to something positive. The aromatic ring has 6 p orbital electrons. All of those are very high energy. Would we expect p orbital electrons to accept more electrons? No, that runs counter to the chemistry of that structure. It's reactive because of the p orbitals, which means it should act as a nucleophile, not an electrophile. How do we know it's going to do a reaction? What's the next word in our system? Substitution. And substitution is an example chemical reaction. So we need to do a chemical reaction where we do a substitution. If we look at the aromatic ring, it's made up of carbons and hydrogens. E we know nothing about except that it's E. So where would we expect E to substitute? For a carbon or for a hydrogen? To substitute for a carbon, what must happen somewhere along the way? What do we have to do? Remove the carbon. How many times is the carbon connected to the structure? Not how many different carbons there are, how many times is an individual carbon connected to the structure? That would be looking at this bond, this bond, this bond, and that bond. That carbon is connected to the structure in 4 different places. So if we were going to do a substitution, carbon or the electrophile for carbon, other way around, carbon for an electrophile, we have to break 4 bonds. Then what else would we have to do? We would have to make 4 bonds. What do you think? Is that easy chemistry? Or does that sound like a lot of things going on? Okay. That sounds like a lot of stuff going on. Maybe instead of breaking out the carbon, we break out a hydrogen. Does that sound easier? Yeah? Why? How many bonds do I have to break? Say again? How many bonds do I need to, what did I ask? Make or break? Break. How many bonds do I need to make? 1. So given the choice, do I want to break 4 bonds and make 4 bonds, or break 1 bond and make 1 bond? Which system do I want to hope for? The 1's probably a good hope. Okay? And if we consider back through all of our chemical reactions, what's the most we've ever done? Two things. That's it. We make 2 sigma bonds in an addition, which results in the loss of a pi bond. We make 1 pi bond by doing what? Breaking 2 sigma bonds. We break a sigma bond and make a new sigma bond, substitution or addition. When we go through and evaluate the chemistry that we have done, it is all very simple. We are never exploring multiple different bond breakage and makage, which is kind of crazy to consider that. It may seem very complex and convoluted, but we're really only doing one or two things. That's it. Okay? So just using electrophilic aromatic substitution and understanding the language of it sets us up with that information right out of the gate. All of those terms are things you should already know. So this isn't new chemistry. It's just applying what you already know. But you must apply, and you must have learned the content from before. With that information, we can now start to do some crazy stuff. We just broke that pi bond, right? That pi bond is broken to make a new bond. We're going to switch to a black structure now. And I now have a new bond to the electrophile. In the process of breaking that bond, though, one of those carbons becomes positive. I also don't want to forget the implied hydrogen. That's using the chemistry that we've already established. You're taking a pi bond and you use the pi bond to donate electrons. Ta-da, there it is. Okay, I don't like that. I've destroyed aromaticity. This is now non-aromatic. Before we were aromatic. So I might want to go through and explain why it's okay to do this. I could do that by showing all the resonance structures. These resonance structures help me to understand why I was allowed to do this goofy chemistry to begin with. And I could do it again. Why do I need to show all of them? That's the point of resonance, is to be able to see and acknowledge that all of those chemistries are present and that we have to be aware of them. All of these are now intermediates. So you could sometimes see brackets put around them, and they get called sigma structures. They get called sigma structures because of the carbon with the new electrophile added to it. That carbon has only sigma bonds. That's why they're called sigma structures. We could also call it tetrahedral, but we already used tetrahedral to explain what was going on in our nucleophilic addition elimination reactions. And so we use new language to separate those two concepts. I want to restore aromaticity. To do that, I'll take the electrons away from the hydrogen to remake the pi bond. What happens? I will get H+ floating around in solution, which makes sense. If I'm going to swap hydrogen for E, if E started positive, hydrogen had better end positive. And this chemistry works because the E positive is more reactive than the H positive. And what we've now done is an electrophilic aromatic substitution. We've changed the substituent on the benzene ring. The rest of this lecture, I honestly don't remember it, goes through and I believe summarizes all of the reagents that could be used to do this. What are all of the E's that could be used? Okay? There's a lot of E's possible out there, a lot of reagents out there. Okay? The next part that we would be concerned about is that how do we speed this? Well, we can speed this by changing the E. We can make the E more positive, i.e. the electrophile more electrophilic. Or we could look at the aromatic ring. The aromatic ring wasn't particularly reactive to begin with. It wasn't a good, strong nucleophile because it didn't have a lot of electrons. They were all occupied in resonance. But if I could alter that structure to put more electrons in, I could speed it up. So how could I alter that structure? What happens if instead of starting with a normal, quote-unquote normal, benzene, I tweak it? and I put a new atom on there, that new atom X has more electrons than the hydrogen that was on our benzene structure. What happens to the benzene if I have an atom X with electrons? Why do benzenes not typically react? Why are they stable? There's no charge when what? When we do resonance. What is special about atom X? What is atom X brought in?
Extra long pair.
A lone pair of electrons. Can lone pair electrons do resonance?
Yes.
Yeah. So what could we potentially do? Maybe it makes it more stable. How would we know? What should we do?
Draw the resonance.
Let's draw the resonance. Let's take the electrons from our atom X and draw them down. What would happen to the very first carbon? It exceeds octet, so we can move the pi bond to here. What's the resulting structure look like? I didn't touch any of the other pi bonds, but now atom X has a positive charge. What happened to that last carbon, this green carbon?
Became negative, it has a lone pair.
Became negatively charged with a lone pair. If it is negatively charged, is it a stronger nucleophile than our benzene? Yeah, because what do nucleophiles do? Donate electrons. So if atom X has electrons, it can force the benzene to react faster. That's kind of neat. And we can see that by drawing resonance. So this becomes ultimately a fun, quote unquote, review of resonance all the way back in Unit 1. How do you apply resonance to explain how a reaction should go faster or slower? That's kind of neat. And there's a variety of things atom X could be. I could have atom X be CH3. I could have atom X be an OH. I could have atom X be a nitrogen. Would I expect different effects? Yeah. And those different effects are going to be based off of charge, size, electronegativity, resonance, and induction. You mean all the same stuff that we've already learned? Yeah, it's kind of neat. This is why it's a massive review topic. How do you apply that logic system that we've been using for the entire semester into new content? It's lovely. And if the answer is you don't, okay, so be it. Okay, but that's the point of EAS. It allows you that opportunity to showcase how much you've learned or how much you have not learned. Hooray! Okay. With that, we're done today. And Wednesday will ultimately just be a review. You can decide how you want that to run. That can be just looking at the sample questions. That could be asking other questions. You can be asking questions about PlayPosit, anything you want. That is your opportunity to try and get things figured out.